spectators, but it seems there will be no unmasking here today. However, my colleagues and I have conferred, and there is a problem on the board right now that took us more than 2 years to prove. So let this be said. The gauntlet has been thrown down, but the faculty have answered, and answered with vigor.
Sorry.
The clip you just saw is from one of the most famous movies of all time, Good Will Hunting. And most of y'all should have seen the movie, and if you haven't, stop this video right now and go watch it first. Now, when you saw this movie, you may have been like myself and asked, what even is a proof, and why does it matter? Because they make such a big deal out of it in this movie and in popular culture in many instances. I'll answer those questions for you. The first thing is, what is a proof? A proof is an in-depth logical argument using mathematical expressions to determine if a statement is true without a doubt under the proposed conditions. So basically, you're trying to demonstrate that a mathematical equation is always true so that it can be used in any circumstance. Now, why does this matter? You could be thinking, we can just use the equations. We already know them. Why do we have to work so hard to compose these proofs? The most important part about proofs is you're able to actually prove that those equations hold. All the equations that you've used growing up in elementary school, middle school, high school, those were all proven at some point to allow you to use them and guarantee that the answers you get are actually true. If the equation's not proven, they may not be true, whatever you come up with using said equation. Now, the main parts of the proof are the statement, the definitions, logical reasoning, and the conclusion. And you will put all of those together, you can come up with a good mathematical proof that can prove that an equation will always hold. So the statement is basically just explaining what you're going to prove and what the circumstances are for what you're going to prove. So for this proof on the right, we're saying that if the function is 1-to-1 and onto, we will prove that the function of the complement of c equals the complement of the function of c. Now, some definitions. You're going to have to define things within your proof to allow you to get to that conclusion. So an example for this would be we have to define onto and 1-to-1, and using those definitions, we're able to get to our conclusion. The logical reasoning is what ties all this together. So by putting the definitions of one piece and another, you're able to go step by step through your proof, logically, and tie it all together so you can come up with a cohesive train of thought. Finally, the conclusion is when you wrap it all up and you tie it back to your statement. So you tie all your logical reasoning and definition together so that you have a conclusion that matches your statement, and therefore your proof is true. So, this class, MA 383, Foundations of Math, how is this class different from any other math classes I've taken? This class focuses on logic, definitions, and a new way of thinking rather than cookie-cutter formulas, which you may have experienced in any other math class, as I did. So an example of a cookie-cutter formula is here from calculus. When you're doing a related rates problem, you have a formula that you're going to do for basically all scenarios, and you're just going to plug in the equations for, the circumference of the circle, or maybe the radius, or whatever the situation may hold. But it's still a cookie-cutter formula that you're plugging and chugging once you've learned the formula and what it means. For this class, Foundations of Math, when you're writing a proof, it focuses on how you think about the problem to come up with a solution, because there's no cookie-cutter formula to writing a proof. The two examples of proofs on the screen here are entirely different, even though they're both proofs in the same class within a month of each other. One is using induction, going through steps of induction, and the other is a direct proof using definitions as the previous one did. So the main difference between this class and other classes is the fact that this class focuses on how you think about the math problems and how you can use logic to prove that they're true, rather than learning formulas, learning what they mean, and just applying them to problems that already exist. You're really working on how you think about math and really defining what it means for something to be true.
So now that you have an understanding of proofs and how this class is different, the problem we're going to be solving today is let A and B be sets. We must prove that the power set of A intersecting B equals the power set of A intersecting the power set of B. So going through the 7 steps of the proof solving process from the wiki proof, the first step is we need to come up with an example that we can test this hypothesis. So for our circumstance, we're assuming that the set of A equals 1, 2, and the set of B equals 2, 3. In that circumstance, the power set of A is the null set, the set of A, the set of 1, and the set of 2. Then the power set of B is the null set, the set of B, the set of 2, and the set of 3. We're then able to take the intersection between A and B, which is the values that both sets share, and we're able to say that the intersection of A intersecting B is 2. Then the power set of A intersecting B would be all possible sets that are included in there, which would just be the null set and the set of 2. Finally, we're able to test if the power set of A intersecting the power set of B, what that equals. And in this circumstance, the only sets that these two power sets share are this null set and the set of 2, which means that the power set of A intersecting B equals the power set of A intersecting the power set of B. So based on our example, the statement we're trying to prove seems to be true. Then we go into the second step of the proof writing process, which is our if-then statement. So to lay this out, we're just going to take our proof and break it up into an if-then statement. So we're saying if C exists in the power set of A intersecting B, then C exists in the power set of A intersecting the power set of B. So we're just taking the same proof and we're rewriting it into a more manageable statement that's understandable. Then step 3 is our no. So the no is whatever is in between the if and the then in your if-then statement. So for us, it's that C exists in the power set of A intersecting B. Then step 4, we're going to expand our no. So using the definitions that we know, using algebra, we're going to expand our no into more manageable pieces so we can compile our proof later. So for us, if we know that C exists in the power set of A intersecting B, we know that C is a subset of A intersecting B by the definition of the power set. We then know that C is a subset of A and B by the definition of intersection. So C is a subset of A and C is a subset of B by the definition of intersection. So now we've broken up into its core components. We then go to step 5, our show. Our show is whatever comes after our then and our if-then statement. So for us, our show is that C exists in the power set of A intersecting the power set of B. Step 6 is to expand our show. So just like we did to the no, we're going to break it up into its core components that we can work with more easily. So for us, it's that C exists in the power set of A and the power set of B, which we know by definition of intersection. And then we can say that C is a subset of A and C is a subset of B due to the definition of a power set. Finally, we're going to take what we got from expanding our no and expanding our show, and we're going to compile it into our if-then statement 2. So for us, it's going to be if C is a subset of A and C is a subset of B, then C is a subset of A and C is a subset of B, which for this proof seems kind of self-explanatory, but we would not have been able to get here without the previous 6 steps. So now we've completed the 7 steps to compile the information necessary to write our proof. We're going to follow the wiki proof writing, and we're going to actually compile the proof. So the first thing we need to do is we need to choose a strategy. And based off what we laid out in our first 7 steps, I'm going to say you can prove this directly, and we don't have to use induction method or proof by a negative, basically. So we're proving this directly in this circumstance. Then we're going to write down our first line. So I laid out a basis for the proof. So I said if A and B are sets, so defining A and B as sets, I will show that the power set of A intersecting B equals the power set of A intersecting the power set of B. And to do this, I'm going to need to show they're subsets of each other in both directions, so we can prove that they're equal. Because if they're both subsets of each other, then they have to be equal. So I'm going to show that the power set of A intersecting B is a subset of the power set of A intersecting the power set of B, and that the power set of A intersecting the power set of B is a subset of power set of A intersecting B. So, in our first direction, we're going to choose our first line. So our first line is going to be assume. So we're showing the reader what we're assuming for this direction of the proof. So assuming that C exists in the power set of A intersecting B, we are then going to clarify to the reader what we want to show. So that's step 3 in our checklist. So I will show that C exists in the power set of A intersecting the power set of B. So we've now laid out to the reader what we're assuming in this direction and what we will show in this direction, and we will to use all the work we did in our first 7 steps of the proof writing process to actually compile the proof together. So these are the nuggets from our know and our show. So we were able to get from the first line, our assume, to the last line, our show. So for this scenario, we said if C exists in the power set of A intersecting B, then C must be a subset of A intersecting B by the definition of the power set. It's important we lay out how we got there by definition of the power set so the reader knows where we got that from. Then, by the definition of the intersection, C is a subset of A and B, right? That's directly the definition of the intersection. So C must be a subset of A and C must be a subset of B. Now we could say that if C is a subset of A and C is a subset of B, by the definition of power set, C must exist in the power set of A and C must exist in the power set of B. Then, by the definition of intersection, we can say that C must exist in the power set of A intersecting the power set of B because C existed in the power set of A and C existed in the power set of B. We're then going to do the other direction and go through the exact same steps in our checklist to make sure that both directions look good. So we're going to say, assuming that C exists in the power set of A intersecting the power set of B, I will show that C exists in the power set of A intersecting B. So this is laying out to the reader once again what we're assuming and what we're going to show by the end of this side of the proof. So if C exists in the power set of A intersecting the power set of B, then C exists in the power set of A and power set of B by the definition of intersection. So C exists in the power set of A and C exists in the power set of B by definition of intersection. So once again, we're laying out how we got there to the reader by the definition of intersection so they know what we used to get to the step and we're not just jumping to conclusions so the reader can follow. Then we're going to say if this is true, then C must be a subset of A and C must be a subset of B by the definition of a power set. So the definition of a power set states that if C exists in that power set, then it must be a subset of that set. Finally, we're going to go to the last 2 steps. So then C must be a subset of A and B. So C was a subset of A and C was a subset of B. So it must be a subset of A and B. So by definition of intersection, C is a subset of A intersecting B. Finally, by the definition of power set, if C is a subset of A intersecting B, C must exist in the power set of A intersecting B. And now we've gone from our initial assumption to what we were trying to show in both directions, and our proof is finished, and we've proved that the power set of A intersecting B equals power set of A intersecting the power set of B. And finally, we're going to quality control our proof using the checklist. So we made sure we defined our variables. We defined that A and B are sets in this scenario. We would have needed to show any algebraic transformations, which we didn't really make in this scenario. We need to make sure we had what we're going to show and what we're assuming. And then we need to make sure that we defined anything we use. So we may need to make sure we had the definition of intersection, the definition of power set laid out every time we used it within this proof.